Chapter 4 is titled Rational Functions. We'll start with Lesson 4.1, Inverse Variation and the Reciprocal Function. In this lesson, we'll determine if a relationship between x and y values represents inverse variation, we'll write equations, we'll look at an inverse variation model, and then we'll begin sketching graphs known as reciprocal functions. First, the definition for inverse variation. The definition for inverse variation is when one variable increases, the other decreases. The template equation for an inverse variation model is the product of x times y equals k, or if you isolate y, you have k divided by x. Now x and y are your variables, which means k is going to be a number, but it's also known as the constant of variation. So k is going to be a number that relates the two variables together. It says, does the table of values represent inverse variation? If so, write the equation for the table. To model the definition or using that template, if we follow the form x times y equals k, we're looking for k to be the same answer no matter what. Taking a look at the x and y values kind of in column form, when x is 1, y is 12. So 1 times 12 equals, 12. If we take the next column, 2 and 6, 2 times 6 also equals 12. 3 times 4, and so on. We have 4 times 3, which is also 12, 6 times 2, and 12 times 1. Since the constant remained the same for all of their products, this does in fact represent inverse variation. So we would say yes. The constant is that product each time, so k equals 12. Therefore, the equation would be x times y, the product of the two variables, always is equal to that constant of 12. And that's when you have a table, how you can determine inverse variation. Over on the right, let's try another model. We have a column of x's and y's, and we want their product to stay the same. If we take that first product of x times y, obviously 1 times 20 will equal 20. But in that second example, we have 2 and 17. 2 times 17 equals 34, which is different than 20. So they don't equal the same constant. Therefore, this is not inverse variation. And if it's not inverse variation, we don't have, there should be none over there. We don't have to write the equation. Other methods used to writing equations, if you're given information that's not in table form, always start with that template xy equals k. Read through the given problem and use information to help solve for k, that constant, and then use it to rewrite the formula. So your answer should never be xy equals k itself. It should always be xy equals whatever that number k represents. Last but not least, if you're asked to find additional solutions, use the formula that you generated to find those additional solutions. Let's take a look at some examples on the right. Example 2, it says, in an inverse variation, x equals 10 when y equals 3. Write an equation to represent the inverse variation, then find the value of y when x equals negative 6. All right, so the first thing we're told to do is start off with the template xy equals k. So we'll use this information in step 1. xy equals k. So to write in our equation in step 2, we want to make sure that we determine what k equals. So we had some given information. When x is 10, y was positive 3. Therefore, 10 times positive 3 is going to equal the constant. In this example, that would equal 30. Now, to use that in the formula, we would have x times y is equal to 30. So notice we don't have k in our answer, we have 30 that represents the value of the constant. Lastly, it says, find the value of y when x is negative 6. So if we want to find the value of y when x is negative 6, we know negative 6 times y should equal our constant, which is 30. To get y by itself, we'll simply divide both sides by -6. 30 divided by -6 would equal -5. So we wrote our equation, we determined the constant, and then we found additional solutions using the formula or the equation that we created. With given word problems, there are other kind of terms that represent modeling inverse variation. You could read something like y varies inversely, which is very similar, but means to do the same thing, or you might see something like y is inversely proportional to x. Those all mean we're going to start with that same xy template, or xy equals k template. For our next example, you are going to want a calculator, so make sure you have one of those ready. It says on a guitar, the string length S varies inversely with the frequency of its vibrations. So right out of the gate, we're given different variables from our template, but we know that they vary inversely. Please underline from S all the way over to F. S varies inversely with the frequency F. So string length varies inversely with the frequency of the vibrations they create. If we start with our model, xy equals k, normally it's y varies inversely with x, so the y value is always the first variable that's written before the phrase varies inversely. So this is like our y variable. Oops, like y. There we go. And what it's varied to would be our input or our x value. It should be like. So like our x value. Instead of x times y equals k, let's use our variables that are represented in the word problem. Instead, we'll go s times f. Oops, did I write that in the right order? I did not. I knew I was going to do that too when I thought about writing this out. So x is like our input, so that's f. Y is the output, so that's s. F times s equals k. That's our template. Now it says the frequency of a 26-inch E string is 329.63 cycles per second. I know, that's pretty interesting stuff. So the 26-inch E string is the string length. So this is our S variable. And the cycles per second would be the vibrations of the frequency that it creates. So that is our F variable. To determine our constant, at least this is pretty easy, we're just going to multiply them together. 329.63 times 26. And all of this is just to get that constant, that number that should stay the same in this equation. If you plug this into your calculator, you should get k equals 8,570.38. That is the k value. So then in kind of general terms, we're going to take our equation and model it for any string length. F times S is going to equal that constant. So that is the equation that'll model any string length and frequency. It then asks, what is the frequency when the string length is 13 inches? So if the string length is cut in half, what's going to happen to the frequency? If we think about what it means to be inverse variation, as one increases, the other decreases, well, if our string length decreased, the frequency should technically increase. Let's put that to the test. If we're given our string length, that's S, if S equals 13, then F times 13 should equal 8,570.38. To get F by itself, we'll divide both sides by 13. I'm going to run out of room here. All right, so the frequency, I'm going to just give myself a little bit of extra space here. If we take our constant divided by our string length, the frequency is approximately 659.26, and we'll just kind of abbreviate the label as CPS for cycles per second. So notice our frequency increased as the string length decreased, and that's inverse variation. All right, everybody, it's your turn. I'd like you to read the word problem for example 3B and see if you can write the equation that represents the given information and then answer the additional question. Once you feel you've created that model and you found the additional solution, press play and then we'll move on to graphing on the back. Okay, let's see how you did. If we model inverse variation with our template xy equals k, the variables that we're including now are time and number of people. So T for time and N for number of people. Time would be your output and N would be your input. The more people you have painting, the less amount of time it should take. If 5 people are on the job painting, it takes 12 hours to paint a particular building. Using that information, 5 times 12 would be a constant of 60. So the first thing I did was generated my formula for this situation. That would be our inverse variation equation. And then it asks you how long will it take if 8 people are painting? Well, if we increase the number of people, it should make sense that it'll take less time. Therefore, if n equals 8, I did 8 times t equals 60, divided both sides by 8, and I got 7.5. And I labeled my answer in hours. It would take less time to paint the house if more people were there to do the job. Domain and range are going to play pretty big roles throughout this topic. So as a quick refresher, remember domain represents x or all possible inputs in your equation. Range would be the y value or all possible outputs. Now, depending on the type of function you have, you might be able to plug anything in you want, or you might only be able to plug in certain values. Over on the right, we have 3 such examples. It says determine the domain and range for each function. In the first example, f of x equals 2x plus 1. This is an example of a line. It's just a linear function. And thinking of lines, they go to the left and right forever. There are no breaks in the line unless it's a vertical line, like straight up and down. But this one has a slope of 2 and a y-intercept of 1. Since it can go to the left and right forever, that means the domain would be x, and it would be all real numbers. You can plug in anything you want for x. Using infinity notation, we would say from negative infinity to positive infinity. The unique thing about linear functions is that the range can have any possible output as well. It can equal any number on the y-axis. So we would pretty much say the same thing, but notice we're not using y. Our output notation is f of x. So we would say f of x also equals all real numbers. And we would use the same infinity notation for the range that we did for the domain. Unfortunately, we're not going to be working with linear functions the entire time. Our functions are going to have some kind of restrictions on them. And if we look at g of x in example B, you'll understand why. It says g of x equals 1 over x. Now x is in the denominator. When you have a fraction, there are certain rules for fractions that we have to be mindful of. In this case, it's that a fraction can't have 0 in the denominator. So that's something that you're going to definitely want to remember for this. Fractions can't have 0 in the denominator. So anytime you have a denominator, we have to note, sorry, it looks like I just kind of scribbled it all out. Let's just put maybe a little star right there. We have to note that the denominator can't ever equal 0. So not the domain, but the denominator. In this case, because it's just x, the only value of x that would make the denominator 0 is in fact 0. So we would say for the domain, as long as x doesn't equal 0, it could be anything else. It could be positive or negative. It could even be a fraction in itself. But then our output would exist. Now, infinity notation is a little trickier on this one. It can't equal 0, but it can equal anything on the left and anything on the right. So infinity notation is going to have 2 parts. From negative infinity, it can approach 0, but we'll use a parenthesis. That means it can't include 0. Then we're going to say the union, from 0, it can go on to positive infinity. But remember, we're not using a bracket on 0, so therefore it can't equal 0. Now, the thing with range kind of like domain, it matches for this particular function. If you have 1 divided by a number, you can never have 1 divided by something and have your output equal 0. So for our range, this is going to be g of x. It also can't equal 0. 1 divided by x would never equal 0. So then we write our infinity notation the exact same way. After this, oops, I forgot the u. There we go. The u means union, means both the left side and the right side. As we get into more unique types of these fractions, the domain and range will change from each other. For our last example, h of x equals 2x plus 6 over 3x minus 4. Now, in this particular example, not only do we have an x in the denominator, which is going to affect our domain, but we have x's in the numerator and denominator, which will affect our range. So this has double duty here. It says, all right, so we'll do domain first. And remember the rule on domain is that the denominator can't equal 0. So it's a little trickier than the last one. Instead of just x, we now know that 3x minus 4 can't equal 0. Well, we need to isolate x, so we'll have to solve this type of equation. I'm simply going to add 4 to the other side, and we have 3x can't equal 4. If you divide by 3, x can't equal 4/3. That is the domain. So it can't equal that fraction. It could be anything else. Notice it can actually be 0 for this one. So this is our domain answer. And then remember, you can write it out with that infinity notation. You could say from negative infinity to positive 4/3. I know this is pretty tedious to write out. I apologize. And then from 4/3 up to positive infinity. Now that's just domain. Range takes on a whole new level for this one. When you have a fraction, and I don't know why I just wrote a mark down there, when you have a fraction that has x's in the numerator and denominator, we take a look at what's called the lead term. So to get the range on this one, the lead term is the term with the biggest x, and in this case, in the numerator, it's 2x. So we're going to use that on top. And in the denominator, we're going to take the biggest term with x in it and put that on the bottom. 2x over 3x. Now, if we simplify this, the x's in fact cancel out, and we get 2/3. But instead of saying the range can equal 2/3, this is actually what it won't be able to equal. So we would say h of x can't equal that 2/3. And that is the restriction on the range. We could actually plug in a value and get 0 for this answer. All right, so then we're going to write negative infinity to 2/3, and then union, make sure I have enough room, 2/3 to infinity. Okay, I think that's plenty for this video. That got a little longer than I anticipated. So go ahead and make sure to upload a picture of your notes for credit.